Alrighty. So you have this table here. This table is representing 9th, 10th, and 11th grade students. And it's like, I guess it's their opinion on something. They have a positive opinion of it, a negative opinion of it, and question mark means whatever, no opinion. So what this 8 here represents is there are 8 ninth graders in the survey who have a positive opinion of something. And here this 4 represents our 9 ninth graders, or 4 ninth graders who have a negative opinion of it. We don't know this, but we can fill it in. Because we're going to try to fill this table in so we can answer some questions. So the first question is kind of how do you fill in this table? And it really just represents data, information surveyed from people. So again, what this represents here are 11th graders who didn't like something. All right, so how do we find out this blank spot? Well, to find out that blank spot, do you understand what this 20 means? That 20 right there means that all of these add up to 20. So could you figure what that would be? If 8, 4, and something equals 20, could you figure that out? Yeah. Hopefully so, because 8 plus 4 is 12, and 12 plus what is 20? So hopefully you can see that would be 8 people have no opinion. 8 of the ninth graders have no opinion on this thing. So let's find out this blank right here. So if we have how many people liked it, well, there's 14 people who had a good opinion of it. So that would be 8 plus 2 is what? 10 plus what would give you 14? 4. You can see that would be 4. All right, let's try this little hole right here. 4 plus 10 plus what would give you 18?
4.
Hopefully you can see that's also 4. All right, let's try this one right here. Okay, we don't know the total, but can we just add up how many 10th graders there are? 2 plus 6 plus 2 is 10. So there are 10 10th graders. This right here adds up all the people who don't like it. So we do have all the information to add down? Yes, we do. So that would be 20. And then this box right here, can we add down again? How many people don't have any opinion? Looks like 14. Now, the question is, what goes here?
The total of all those added up.
Total of everything. Total people in surveyed. So does it matter if I go across this way or down? Should they be the same? Okay, if we go down here, can you see that's 48? If you go across, you also see it's 48. So this right here is the total number of people in the survey. We just filled out the table. Sometimes the table's done and then you just answer questions. Sometimes you have to make the table yourself. We just this is one that we had to fill in some gaps. Alrighty. How many ninth graders had no opinion? So we got to look for no opinion. No opinion. Wait, which was no opinion? Positive, negative, or question mark? Question mark, and then they didn't really have opinion. They're like, whatever, I don't have it. I don't know. So it was how many ninth graders had no opinion? Now there are 14 no opinions, correct? But how many of those are ninth graders? 8. So you just put 8. All right. How many 11th graders had no opinion? So we go to no opinion again. 11th graders is right there. So that would be 10. Oh, no, I did it wrong.
Yeah, 4, right?
Down the no opinion, so it would be 4. I did the negative opinion. So that would be 4. And then the last one is, how many students did not like it? Oh, did not like it. Well, that would be the negatives. So all of those, so I can just look at the bottom, would be 20. So that right there is how you kind of look at it. You can look at it anything. I can make any statement up. For instance, what does this one represent? Well, it represents 10th graders that had a good opinion of it, that liked it. Every single spot you can make a sentence for. Make sure you could do that. If I point to something, could you write a sentence or know what that is describing? That's important. So it's called a frequency table because it's how frequent something happens. How frequent it happens, frequency. All right, these last 2 questions deal with probability, the likelihood of something. So what is the joint relative frequency for ninth graders that liked it? So probability is what you want out of what's possible. It's a fraction. So the question here is ninth graders that liked it. So how many ninth graders liked it? So ninth graders had liked it. Is it 8? So that would be 8 out of, well, how many people were in the survey? Out of the whole survey? 48. It's just a fraction. So what is the joint relative frequency of ninth graders that liked it? So there were 8 ninth graders that liked it. So how many ninth graders that liked it are there? 8 out of the 48. So what percent of the population is this? Or what fraction is it? So we just reduce this fraction. Okay. And 8 goes into 48 6 times. So it's 1 in every 6. Which you could get a decimal. And could your calculator reduce that for you? There you are. That's the likelihood. 1 in every 6 people in this survey, if it's accurate, are ninth graders that liked it. Okay. Let's try this next one. Joint relative frequency of 10th graders that did not like it. So how many 10th graders did not like it? So if a 10th grader, that was negative, so that'd be 6. So that's 6 out of the 48, which is, when you reduce, 1/8. So 1/8 of them surveyed are 10th graders, and they did not like it. That's what you could find probabilities with this out of the whole. And that's what probability is, what you want out of the whole possibilities. What I have here on this problem here, I have some data. I want to make a dot plot. Here's the data I have. And a dot plot is kind of like a bar graph, is what you did as a kid. So we're going to make a picture of this data. So we're looking at these numbers. We basically do it by making a number line. So I'm going to start with a number line. All right, I'm going to go, okay. What's my lowest number on in this data? See, my lowest number is a 2. What's my highest number? 10. So I need to make a number line that goes from 2s to 10s. So I can just go, okay, I'll make that a 2. I'm going to make it every other to save myself some space. 2, 4, 6, 8, and 10. So I could have put every single number, but I need from 2 to... So next step is to put each number as a dot on the graph. Now, some tests make an X. I put a dot. So I put a dot at 3. So I go over here and I put a dot at 3, with 3 would be in the middle. Okay, there's a dot. So I got that one done. Put a 5. So I go to 5 and put a dot. 5's in the middle here. Got it. I have another 5. Okay, I'll put the 5 on top of that one. Are you guys okay with that? I'm stacking them. Okay, 3. Oh, go back and stack that on top of this one. All right, 5 again. Oh, another one. Okay. Stack that right there. 2. Haven't had a 2 yet. Okay, put there a 2. 10. Okay, put my 10 right there at 10. Another 5. Okay, one more 5. And a 3, which we've had a 3. There we go. So what I did is I took every data, kind of nice to cross them out as you go to make sure you've done them all. There is all my data stacked up. It kind of makes a bar graph, which is another thing we're going to be focusing on as well. Bar graph, dot plot, same kind of idea. All right, so how is the data skewed? Well, look at this data. Skewed means there's a value that's kind of like not normal. It's kind of out there. It's called an outlier. So if something's skewed, it has something called an outlier that's kind of out there, that's kind of different than the rest. Can you see one of these numbers that doesn't seem to match? Something seems weird about it in comparison to the rest. Which one is it? Can you tell that 10 is a little weird? It's kind of out there all by itself. So how is the data skewed? Well, that number 10 has skewed it. It's an outlier. And what has number 10 done? It has skewed it to the right. So that number 10 has skewed it, has messed it up to the right. Meaning, if we didn't have that 10, if we crossed it out, would all my data be pretty much here? But what that did is it kind of said, hey, over here, I'm going to pull you over a little bit because I just don't fit the norm, the normal look. So it has skewed it. This number 10 has an outlier that skewed it to the right. Alrighty. So here's some data. The first thing you do when you have data is, Wait, by the way, could I make a box plot, a dot plot with this data?
Yes.
Yes. Could you tell that 20 would be out of the ordinary?
Yes.
Okay. But for what we're doing here, what we want to do first is we want to put it from lowest to highest. Okay? So I want to put it from lowest to highest. So what would be my lowest number? Looks like a 1. And then I cross it out so I don't do it twice. What's my next lowest? Is that a 2? You're just putting it from lowest to highest. And you want to cross it out so you don't miss one. What's next? 3. Next will be 5. I have 2 of them, so I have 2 5s. 3 5s, so I put 5, 5, and 5. Okay, then I have a 6, a 7, and a 20. Do you see where crossing them out is important? Otherwise, you might do it too many times, too few times, skip something. Let's double check. How many numbers do I have? It looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's count here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 numbers to start with. I have 9 numbers to end. I now have them in order. That is how everything starts. You have to start by putting them in. Okay, to get the mean, median, and mode, let's first talk about what each one is. The mean, a better name for that is called your average. More common name is average. The median, a better name for that is the middle. And the mode, a more common name for mode, is the most often. So the most, or you can say most often. So those, we're going to find the middle of this data, the most often, and the average of this data. Okay, how do you find the average? Well, do you remember to find the average, you add them up and divide by how many? So what we're going to do is going to add all those numbers up, which is kind of annoying. I got to go 1 plus 2 plus 3 plus 5 plus 5 plus 5 plus 6, plus 7 plus 20. And how many numbers did we say we had? 9. So you add those all up, and you're going to divide by 9. Now, I'll just tell you, when you add those up, you're going to get 54, and the bottom stays 9. And 54 divided by 9 is 6. So my average of all these numbers is 6. All right, if I want the median, it's the middle. So we got to find the middle of this data. So is there one number in the middle, or do I have to find the middle of 2 numbers? Well, let's look. If I have 9 numbers, where's the middle? Well, can you see, is the middle somewhere in here? Okay, can you kind of find the middle? Is the middle right here or here? Well, if we have 9 numbers, wouldn't that mean I have 4 on each side?
No.
Does that number right there have 4 numbers on each side?
Yes, so it'd be 5.
So can you tell, did I do this right? Is that 5 in the middle of the data?
Yes.
Is there 4 on the left and 4 on the right? So the middle is a 5. That's all median is. It's the middle value. Now, do you see how it's very important you put in order? The middle of this data makes no difference. It's just random information. But the middle is right there. And the most often, that's exactly what it is. The mode is the most often. So what came up most? Oh, 5 also came up the most. So that's how you describe mean, median, mode. The mean takes the most work. It's mean. It's the average. Takes the most work. It's the mean one. The other ones are pretty easy to get. The range, what is the range? The range is the span from the largest to the smallest number. Okay? It's the difference from the largest to the smallest. So what I'm basically going to do for the range is I'm going to take the largest number and I'm going to subtract the smallest. The range will give me how far it is from high to low. So what's my biggest number? 20. And my smallest is a 1. So what does that give me? I have a 19 range. The range, again, is how far from this number to this number. The span. From my lowest to my highest, I have a 19 different span. Next one, we have this Q1, Q2, and Q3. Q's are quartiles. See this word interquartile? It's a quartile. It's a marking. So Q1, Q2, and Q3. What Q2 is really just your median. So put the same number as your median. It's always just right there. So Q2 is just your median, which in this situation is 5. What is Q1? Q1 is the middle of the left side. So for Q1, we're going to find the median of the left side. So the left side, that's over here, the 5's in the middle, I want to find the middle of this. So if you look at that real carefully, we have 1, 2, 3, and 5. I want the middle of the left side. Isn't that the left side? I want the middle of that. So the middle of that, well, isn't it right here? Isn't right here the middle?
It's 2.5.
So we have to find the middle of that. Now some of you can see it's 2.5, but how do we do that? We have to take the average of 2 and 3. So to find the middle of the left side, I have to take the average of that. So that would be 2 plus 3 divided by 2. It's the average of 2 and 3, which is 5 divided by 2, which is 2.5. So my Q2 is 2.5. Again, your Q2, sorry, I said that wrong, my Q1. Q2 is the middle. Q1 is the middle of the left side. What do you think Q3 is? The middle of the right side. So could we also find the middle of the right side? So we have, that would be 5, 6, 7, and 20. Can you find the middle of this side? Some of you can just look at that and see it's 6.5. But if you can't, what you do is you take 6 plus 7 and average it, which is 6.5. So my Q's are the middle of the data, and the middle of the left, and the middle of the right. That's how you find quartiles. And they have a reason behind them, but right now we're just finding them. Next, did you see we had range up here? That was the highest minus the lowest value. The interquartile range is the same thing, but you're using the quartiles. So all this is going to be is the highest quartile minus the lowest quartile. Can you take Q3 and subtract Q1? It's from the highest to the lowest quartiles. So that would be, the highest quartile is 6.5 minus the smallest quartile, which is 2.5. When you subtract the 2, you get 4. So my interquartile range is from 6.5 to 2.5, which is a span of 4. I want to do something called a box and whiskers. It's a way to graph data. We use a coordinate plane to graph functions. We're going to graph data on a number line. So here, we're going to graph this data on a number line. So for my number line, my lowest number is 1. My highest number is 20. So actually, I'm going to start with 0 here. And I'm going to go by 5s. 5, 10, 15, 20. I'm going to make a number line going by 5s. And I'm going to put my important data on it. I'm not going to do a box plot. I'm going to put my important data. I'm going to start with my Q's. My Q1, my Q2, my Q3. So I'm going to put my Q1. What was my Q1? It was 2.5. So 2.5 is right about there. Are we okay with that? So my next one is my Q2. My Q2 is 5. So you put a line at 5. Trying to make a box here. And my next one is Q3, which is 6.5. So I put another line at 6.5, which is to be somewhere maybe around there. And then we're going to make a box out of all that. So I got for my thing, this is going to be Q1, Q2, and Q3. Make sure you label those. Q1, Q2, Q3 are how we make our box. All right, now I need whiskers. Your whiskers are your edge values. Your whiskers are the values on the edge. So my lowest value altogether was a 1. So I'm going to go down here, put a 1, and then I'm going to put a whisker. It's a line connecting it. So that's your lowest value. And my biggest value was a 20. There we go. So this is your highest value. And this is your lowest value. So all we're doing is plotting our Q1, 2, and 3 and our lowest and highest value. This is your box, and these things are called your whiskers. We just did a plot of this information. See, we got all these on it, and it shows some very important information. We want to find the outlier and this sentence right here. Outliers are things that stand out, that are kind of way out there, they're kind of not following the rest of the data. And the 20 is your outlier. Can you tell the outlier is skewing it which direction? Right. Can you see right here how this is way the heck skewing, pulling this whisker really far to the right? Now, the next question is kind of interesting. How does the outlier affect the mean in relationship to the median? Meaning, how does the outlier affect your average? Would it change the average?
Yeah.
Would this outlier, if I took it off, if I took 20 out of here, would that completely change your average?
Yes.
My average was 6, right? If I took 20 out of this, you cross that out right there, would that lower it quite a bit? So what did the 20 do? Didn't it make your average bigger than it should be? Okay. So if my mean, is this my mean, right? Is this my median? My median's right here, right? My average is right here. Is my average right here? If I took 20 out, would that get closer to my median or farther away? Are you okay? Right here at 6 is my average. But if I took 20 out, wouldn't that shrink and bring your average closer to your median? So how does the outlier affect the mean in relation to the median? It brings it closer to the median. What an outlier does is if it pulls it away from the median. An outlier pulls it away from the median. So an outlier pulls the mean away from the median. Normally, the mean and median should be kind of close. But if you have an outlier, all of a sudden the mean gets pulled left or right of the median. And as you see here, isn't the average, the mean, on the right side of the median? If there's an outlier on the right side, it's going to pull it to the right side of the median. If the outlier is on the left side, it's going to pull it to the left side of the median. It pulls it left or right away from where the middle of it is. Last thing here is we're going to do the line of best fit. So I'm going to put this data on this graph. I first got to decide, I have age and height. I got to decide if I want to put age or height on which axes. And I'm usually, don't we put X here and Y here? So I'm going to put age is my X. So can I put my ages? I'm going to just start at 13. And then I have 14, 15, 16, 17, and 18. Let's put the little squiggly. Remember the little squiggly thingy? To remind you we started there. And my heights, well, if I have heights here, I go from 61 all the way to 65, correct? So what do you think I want to go by here? Well, if I'm going from 61 to 65, could I put a little squiggly thing again and just start maybe with, call this 60. Wouldn't this be 61, 62, 63, 64, 65? So let me kind of describe this again. This is age. And what is the red? It is your height. I am making a graph from this data of people. I have different ages. I have heights. I have ages and I have heights. Okay. And I'm going to plot this data on this axis. My x-axis is my age. My y-axis is my height. We could think of these as the average height, maybe, or it could just be a survey of a handful of people. We're going to plot these data and then make a line to best fit it. Next, we're going to put data plots. So at 13, we put a 61. So at 13, I'm going to put a dot at 61. I was putting each dot. At 14, I'm going to put a 63. At 15, I'm going to put a 64. At 16, I'm going to put a 64. At 17, I'm going to put a 65. And at 18, I'm going to put a 65. Now, those, I guess, are inches in heights. So right here, I have a set of data of some heights per age. And I want to see if I can see a trend. Can you see a trend? As people get older, are they getting taller? Now, that's pretty obvious because we live in a society, in a world, as you get older, you get taller. But is there a point where you actually stop growing usually? Yeah, when you get older. But for this scenario, for what we see, do you see, this is called a positive correlation. I'm going to write that down. This is called a positive correlation. Why do you think we call it a positive correlation? Well, isn't it positively growing? Its correlation is, what's the trend? Can you see it's positive? It's going up. Could you have negative correlations sometimes if it's going down? Could you also have just stuff that's scattered all over the place and makes no correlation at all? That's what we're going to run into today. You run into problems that could have no correlation. They don't look like they're going up. They don't look like they're going down. They just look random. But a lot of times data has a way it's trending, either up or down. So here's what we're going to do next. We're going to try to create a line through this data. So then we can make an equation for that line to see about an equation that represents information. I'm going to try to make a line through this data. I want half the data below and half above. So if can you tell, let me see, I'm going to go right here. If I start, oops, I want to undo that. I'm just going to try to freehand a line, and this is going to look terrible. If I start at 61, that kind of looks in the middle. If I make a line, it might get a kind of a straight line. Does that look like I have about half the data above, half below? Would you agree that line looks like about in the middle? Half below, half above, about half the information. It's kind of in the middle of it all. I'm going to go with that line right there. Now, that's what you do. So what you first do is you make your data points, and then you look at those, and you kind of think, okay, where's a line going through it? Do you see how there's a positive slope to this? How do you make an equation of a line? Well, you got to find 2 points. So can I take this as a point right here? Are you okay with that? And another point is right here, and another point is right here. Actually, I like these. Do you like these 2 points the best right here? Are those 2 good little points? So what are those points? Let's write them as coordinates. That would be 1664 and 1765. I'm going to ignore this dot right here. I'm going to look at these 2 dots. From these 2 dots, could you make an equation of a line? Do you see that? I have 1664 and 1765. Can I make an equation of a line from those 2 dots? We did this earlier in the year. Let's make an equation of a line. So I want to make the equation of a line. Don't you need a slope to make the equation of a line? Remember, it's y equals mx plus b. So let's find our slope. Won't it be 65 minus 64 over 17 minus 16? Don't you take the y's over the x's? So what's 65 minus 64? Isn't that 1? And what's 17 minus 16? Is that also 1? So guess what? My slope is 1. Meaning, what that means is every year, does a person tend to get 1 inch taller, according to this information? Every year, it looks like these people are getting 1 inch taller, on average, for this set of data. That's what that 1 represents. I took the slope, again, of these 2 coordinates, which are those 2 dots right there in blue. How do you find b now? Do you guys remember how to find b? Could I take either of these points? I'm going to take this coordinate. Could I put 64 for y, 1 for m, 16 for x, and solve for b. I took, again, just a reminder, x, y, and m. Put them all together to find b. So 1 times 16 is 16. How do you get b by itself? Well, you minus 16 over. So b equals, what's 64 minus 16? Well, what is it? Is it 40? If we minus, put a 1 there, borrow, that would be 14, so it would be 8. Is it 48? So my equation is going to be y equals 1x plus 48.
Wait, are you minusing 18 by the other side, or is that 16?
So I'm minusing the 16 over,
Oh, okay.
and I get 48. So I start with x, y, and m, find b. Now, the weird thing about this graph, it doesn't make sense forever. For these set of data from a high school age, for high school age students, this graph might make sense. For instance, if I plug in 12, could I find out the average age if this is accurate? You could plug it in. Now, what's weird about this graph, it's kind of stupid. If I put in 0 there, when you're born, let's say age 1. If I put 1, a 1-year-old in here, does this make any sense?
Yes.
Have any of you ever seen a 49-inch tall 1-year-old? When you're born, you're usually somewhere in the 20s or so. This would be like a huge baby. So, is this graph good for young kids? No, young kids grow quicker. But for high school kids, if this was accurate, this would depict high school age possible kids' heights. If I had enough data and I made a line to it, I could use my equation to predict heights of high school kids. Would this make sense if I put an 80-year-old person in here? If I put an 80-year-old person in there, would that make sense for an 80-year-old? No. Do you understand this graph only works for a range that we're looking at? We don't know beyond that, really, because we cannot predict that. And especially in life, people grow differently at different ages. Especially when you're 80, you're not growing anymore. You're probably shrinking.